Hi, this is part 2 of titrations. In the first video of titrations, we talked about how to find the pH when we titrate a weak acid with a strong base or a weak base with a strong acid. And what we're going to talk about in this video is how to choose an appropriate indicator and also how to calculate the pH when it's halfway to the equivalence point. There's a long way to do that, and then there's a nice little shortcut. Okay, so this part here that I have at the very top is the most important part on this page. An indicator should be chosen that has a pKa as close to the pH of the equivalence point as possible. The closer you can get to it, the better. Ideally, you want it to be within a value of +1 or -1 away from that pKa. And just remember the pKa is the negative log of your Ka. All right, so here you're given a table and you're given different indicators. At the beginning of the year, we did a titration lab where we used phenolphthalein. That turned that preferably light pink, but in some cases, bright purple pink if you over titrated. And so it turned that color. It has a pKa of 9.3. Now, we happen to use that for a strong acid, strong base, but there are many other different types of titrations for which it would be more suitable. In our case, it was sufficient, but it's even better in other situations. All right, so if I have these different indicators right here, so for instance, methyl orange has a pKa of 3.7, and what that means to us is that if we have an equivalence point, and that equivalence point has a pH anywhere between 2.7 to 4.7, okay, so one up or one down away from this pKa, if it has an equivalence point with a pH in this range, this will be a really good indicator for that reaction. Methyl red is 5.1, so if you have anywhere between 4.1 to 6.1, as your equivalence point pH, this is going to be a good indicator for that. Bromothiamyl blue, 6.0 to 8.0 would be ideal. And then phenolphthalein, 8.3 up to 10.3. And we look at phenolphthalein right now and see the ideal range. We can see why it was so difficult to catch that phenolphthalein right when it was barely that pink color. And that's because it truly does not turn a pH, it does not turn bright pink until it's at a pH of 9.3. Now, we know that when you do a titration, you get this rapid increase in pH. And so we're talking like a portion of a drop will take it from here to here. That's why this indicator can work in that situation. Okay, so we're being told that we have this reaction right here, and we're told that at the equivalence point, the pH is going to be approximately 9. So what would be our best indicator? Well, according to what we have here, we want to pick something that has a pKa really close to this value. And so in this case, the phenolphthalein would be great. Now, if we go back to the titration problems that you did earlier in this handout, so in question 1, we determined that the pH would be 10.85 at the equivalence point. So I'll try to keep this table available for us. Okay, so for titration 1, we said the pH was 10.85. And so we really don't have anything that falls within that range. The closest one would be phenolphthalein, which we said is going to be ideal from 8.3 up to 10.3. This is above that, so phenolphthalein, but really none. None would be ideal in this instance. Okay, titration 2. This was problem 2. We did the titration. we said the pH would be 5.38. So if we go back to titration 2, just to show you where I'm getting these numbers. Okay, titration 2, the pH would be 5.38 at the equivalence point. And so in that case, if it's 5.38, methyl red is going to be our best indicator. We want the pH to be as close to one of these as possible, but it definitely needs to be within that 1 plus or 1 minus range. Okay, titration 3, we said the pH for titration 3 was 7.61. So the bromothiamyl blue would be good for that. And then for 8, so for 8, we had a pH of 5.98. And so in this case, methyl red would be a good choice. Okay, so that's how you choose an appropriate indicator. All right, the next thing we need to talk about is calculating the pH when we're halfway to the equivalence point. I'm going to show you the long way and the short way for number 9. So we're going to do number 9. We're going to do halfway to the equivalence point. I'm going to cram a lot in here. Okay, I'm going to start by writing my reaction. And for my reaction here, I have hydrocyanic acid with sodium hydroxide. So here's my reaction, HCN plus NaOH. And this forms water. So acids are hydrogen donors. And it forms sodium cyanide. You could write as a double displacement reaction, or just remember acids are hydrogen donors, so the H is going over here to the OH, and then your Na is going to be a spectator. All right, so what do we know about the HCN? We know that we have 0.016 liters. And we know we have 0.0320 concentration. Okay, it's being titrated with NaOH at a concentration of 1.024. We don't know the volume. Okay, let's just start by calculating the amount of HCN that would be titrated if we used up all of this HCN. So I'm going to calculate the total moles. And just remember, molarity equals moles per liter. So molarity times liters equals moles. So I'm just going to multiply these together. And this gives me 0.000512 moles total of the HCN. Okay, we're going halfway to the equivalence point, which means if this is my analyte, I'm going to add enough to titrate half of it. So I'm going to subtract half of this, which would be 0.000256. Okay, those are the moles that are being reacted. Okay, and so at this point in time, inside my flask, I've only reacted half of it. And so I have 0.000256 moles left over, unreacted, remaining. Okay, let's look at the NaOH. So the NaOH is in the burette. We can add as much as we need. Well, we need to react half of the moles. So we need to react this amount of our moles. So we're going to add to our flask 0.000256 moles added to the flask. And all of it that we've added is reacting with these number of moles of our HCN. Okay, so essentially everything that we poured out of the burette has reacted. There isn't any left over that's unreacted. All right, so that's from my reactants. Now, as I combine these together and they react, they are making products. If this is a 1-to-1-to-1 ratio, my limiting moles tells me that I'm going to form 0.000256 moles formed of the NaCN. Okay, so we know moles left over of the HCN. We know the moles formed of the CN. And if we're going to find pH, notice that we have here, we have HCN, which is a weak acid, and we have NaCN, which is the conjugate. And so because we have two different components, and these two components happen to make up a buffer. This is an induced buffer. You have an induced buffer as long as you have some of your weak acid or your weak base remaining, and then you have its conjugate that's formed. So in this case, we have half of this acid left over. We have half of the conjugate formed, so we do have a buffer. Now from here, I can take my moles and I can find my concentration. Just remember, in order to do this, we need to have the total volume. And if I know molarity equals moles per liter, and I do the Thomson switch, liters equals moles divided by molarity, I can take this molarity for the NaOH and the moles for the NaOH, and I can get the volume for the NaOH is 0.0025. That gives me a total volume, because remember, concentration depends upon the volume. If there is less of a volume or smaller volume, it's going to be more concentrated. So we've added more solution, so the volume goes up. This gives me 0.0185 liters. So from here, I have 0.0138 molar CN minus. Okay, so this is one component of my buffer, the conjugate base. When I look at the HCN, I have this number of moles. And then once again, I do have to use the total volume, which is 0.00, or 1 extra 0, 0.0185. And so the concentration of my HCN is the same. Okay, that's because half of the moles are left over, half of the moles are formed, and because you've added these two solutions together, they're both sitting in the same volume. And so they're both going to have the same concentration. Because we have a buffer, we know the pH equals the pKa plus the log of our conjugate base divided by our acid, our weak acid. And we would need to know the Ka for HCN. And the Ka for HCN, I can look in my table, and it's 6.2 times 10 to the negative 10. Okay, pKa is the negative log of this number right here. And so my pKa is 9.21. All right, so now I can plug it into my Henderson-Hasselbalch, which is what I use for buffers. So the pH equals the pKa, which we said is 9.21, plus the log. Our conjugate base was 0.0138 divided by our acid, which was the same. 0.0138 divided by itself is 1. The log of 1 is 0. So the pH equals 9.21. This is the long way. The easier way to do this problem is to know that halfway to the equivalence point, the pH equals the pKa for your weak acid, or if you have a base, the pOH equals the pKb. Okay, so number 10, you should be able to now solve that one. And number 11 and 12 as well. You can do it the short way, or if you really want to do the long way, you can do that as well. Okay. All right, from here we can figure out, use our Henderson-Hasselbalch. If we know it's a strong, weak titration, which is going to cause an induced buffer, it's going to create a buffer as long as you have some of both components. And so if that's happening, and we know the Ka, from there we can find the concentrations of our different species. So in this case, this is asking what is the acid when the pH of the weak acid strong base titration has a pH of 3.14 at halfway to the equivalence point. And so you really want to think of this like a puzzle. Okay, and we know that halfway to the equivalence point, these are going to be the same. And the log of 1, because these divide out to give you 1, is 0. So we know the pH equals the pKa. So if the pH we're being told is 3.14, pKa equals 3.14. If we know the pKa, we can find the Ka. Remember, the pKa is the negative log of your Ka. And so 10 to the negative of your pKa, just like we did earlier. So 10 to the negative of your pKa will equal your Ka. And so if my pKa is 3.14, this gives me a Ka of 1.29. Wait, wrong one. This gives me 7.24 times 10 to the negative 4. And so what I can do from here is I can look at my table, the table that I gave you that looks like this. And we're looking for a Ka that is close to that value. So we said 7.24 times 10 to the negative 4. So we're looking for something close to that. 7.24 times 10 to the negative 4. This is probably hydrofluoric acid, HF. Okay, so what is the acid? Most likely HF. So if we know these other pieces to our puzzle, and we know it's halfway to the equivalence point, we can determine the acid. So you should be able to do that for the next couple problems. Okay, the last thing on here is looking at a polyprotic titration. And when you have a polyprotic acid, what happens is it donates its hydrogen one at a time. So let me show you what that would look like. So if I had H3PO4 and I titrated it with sodium hydroxide, acids are hydrogen donors. So it's going to donate this hydrogen one at a time. And so when it does that, it's going to make H2O. And then it's also going to donate one of these hydrogens. So then you're going to get NaH2PO4. This is a spectator ion here, the Na. So you can just write it as H2PO4 minus 2. Or wait, other way around, minus 1. Okay, so that would be the first titration. Okay, then what happens is there's a second titration that occurs as we continue to add sodium hydroxide. And so you have this H2PO4. As we continue to add the sodium hydroxide, it reacts. And this is going to make water. And when it does that, this forms Na2HPO4. Okay, so what we're doing essentially is we're pulling off one hydrogen at a time. We had H3PO4, now we have H2PO4. We have H2PO4, now we have HPO4, minus 2. Every time we take away a positive, it becomes more negative. This would be the second titration, and then this will be titrated. I'll write it without the spectator. Okay, and so when you look at the graph, what you see is this. So at halfway to the equivalence point, you have half of this left over, and you have half of this formed. And so those are equal concentrations. And that's showing that to you right here. So if I'm looking at this right here, it's showing H3PO4 plus NaOH. And so at the first titration, halfway to the equivalence point, I'll scroll down so you can see these numbers here. Okay, so at halfway to the equivalence point, the H3PO4 and the H2PO4 are equal concentrations. Half of this is left over, half of this is formed. Now, when you have your equivalence point, it's usually right in the middle of that where it jumps up. So notice here, this is where it's jumping up. It's not going quite straight up because this is a weak acid. And that halfway mark where it's jumping up is the equivalence point. So it takes 50 milliliters for all of this to titrate in the first equivalence, which means the half equivalence is only 25 milliliters. One full equivalence is 50, one half is 25. Okay, so that's the half equivalence point. At the end of that titration, you'll recall from what we wrote here, where'd it go? Okay, so at the end of the titration, after these have all reacted, you're left with just this. And so that's what that is showing you right here. At the first equivalence point, you have just this. Don't worry about pH calculations. They took that out of the AP curriculum, unless you really, really want to do it. And if so, let me know. All right, the second half equivalence point, that's where we have half of this left over and half of this formed. Okay, and so at this point, the H2PO4 minus equals the HPO4 minus 2. Then we have our second equivalence point. That's where it jumps up, shoots up here. And right in the middle of that, we have HPO4 that's left over. Don't worry about the pH. Okay, the third equivalence point is kind of hard to see here. You tend to see this, especially with something that's triprotic, where it has 3 hydrogens to donate. It's not really this big steep slope right here, and that's because we have so much of this conjugate that's formed at this point. You don't see a massive steep increase in your pH. It's much more of a gradual change. And so this actually indicates our third equivalence point, which means this is going to be halfway to that third equivalence point. So halfway to the third, we have half of this and half of this. And at the third equivalence point, we have just the PO4 minus 3. What I have over here on the right, this is a diprotic. So you should be able to look at one of these and determine the number of hydrogens within the acid. There's 3 of these, so that's how we know this is triprotic. This one, we have 2 jumps, and so this means this is diprotic. They might want you to know something like that. Halfway, because we have half left over, half formed. At the equivalence point, all of this is formed. Half equivalence point, half left over, half formed, and then what we have after we've lost all of our hydrogens here. Okay, so you should be able to give the major species just depending upon what we put right here. Okay, these are the species here that you need to put for all of these down here. So at the beginning of the titration, we had our H3PO4, and we had NaOH that we were adding. And then at the half equivalence point, we have H3PO4, and we had the H2PO4 minus. Okay, first equivalence point, we had the H2PO4. Throughout all of this, when you have these reactions, we do have Na plus forming. So all of these reactions are forming Na plus. So when we talk about these titrations, this is by far going to be the most common species. When we're looking at the acid species, that's going to be either this, 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 or what you have when it's deprotonated. Okay, and then, so I think you should be able to finish the rest of these here. Okay, at the end of the titration, we're left with PO4 minus 3. All of the H plus and all of the OH have gone on to form water. Because we do have this spectator ion, and there's a ton of it because it was present at every step of the deprotonation coming from the NaOH. This is going to be in the highest amount. This is going to be in the lowest amount. Just be careful. This is all relative. I'm talking about total species minus water. This is highest. This is lowest if we're looking at this titration right here. Okay, so that's how you solve titrations. Polyprotic, not such a big emphasis. Might see a multiple choice question related to that.